Today I'm going to talk about how to construct accurate and honest approximation of correlated qubit noise. As we all know, accurate noise modeling is important for designing reliable and practical quantum error correction code, as the performance of quantum error correction code depends on the underlying assumption of the noise model. And knowledge about noise of quantum device can be obtained, for example, by doing theoretical modeling such as Lindblad master equation simulation, or doing experimental characterization such as process tomography, randomized benchmarking, and Lindblad tomography. However, such theoretical simulations and experimental characterization require resources that scales exponentially with the number of qubits, thereby making it impractical for large quantum devices. So the question here is, how can one use full characterization of noise in small quantum processors in order to accurately access the performance of large quantum systems? One strategy to model noise in a large quantum device is to assume the Pauli's noise model. However, this may not be an honest or accurate description of the real noise because it does not capture the chorus noise, which can be the dominant noise in the quantum device. So in this talk, I will present a general systematic way of constructing approximate noise model beyond the Pauli noise, so which is based on the Lindblad noise model. So the usual starting point to describe noise is Lindblad master equation, which describes the evolution of system interacting with the environment. So the Lindbladian here, L, can include coherent noise and incoherent noise. The coherent noise here, which is captured in the Hamiltonian, can include leakage, crosstalk due to always-on qubit-qubit coupling or pulse miscalibration, while on the other hand, the incoherent noise here is captured by the jump or Lindblad operators, such as the decay and dephasing operators. And to describe the dynamics due to only the unwanted noise, we can extract out the unitary, the target unitary, from the exact propagator here, which leaves us a noise channel in the normal form. And from there, we can also get the Lindbladian generator in the normal form. So from now on, I will write the noise channel and the Lindbladian generator in the normal form. And this, again, the actual noise, Lindblad noise here can be obtained from doing the full simulation of the Lindblad master equation or from experimental characterization. Here in this talk, I'll focus on getting this Lindbladian from the full simulation, which will serve as the input for constructing the approximate noise model. So to construct the approximate noise model, we propose a new approach called the cluster expansion approach, which is basically a perturbative series expansion to decompose noise into components based on its interqubit correlation degrees. For example, for a 3-qubit processor, we can decompose the actual noise here into different correlated terms here, 1 body, 2 body, up to the 3 body terms. And each of these terms here can be obtained from this formula here. So what this formula tells you is that the m-order correlated noise terms among qubits in m-qubit subset Sm here can be obtained basically by doing first a partial trace of the actual noise over the qubits outside the subset Sm. And so this partial trace here will give you the Lindbladian that describes the noise in m-qubit subsystem, which also actually include all the lower order correlated noise from the 1 body up to m-1 body, which have to be subtracted from in order to get the pure m-order correlated noise. And next, using these decomposed Lindbladians, we can construct the approximate noise channel by simply truncating the cluster expansion up to the Kate order, if you want to get a Kate order approximate noise channel, and then you exponential each of the Lindbladian components. So for example, the first order approximate noise channel is obtained by just taking all the first order terms. If you want to get the second order approximate noise channel, you include all the terms up to the second order and so on and so forth. And as an example of how to apply our noise model, we consider, before that, I'll forget to mention that this G here is the parameter which makes our noise channel honest and as accurate as possible. So what are honesty and accuracies? So as in the literature, we define the accuracy and honesty in terms of the distances between 3 different density matrices resulting from 3 different quantum channels: ideal or noiseless channel, actual channel, and the approximate noise channel. So so approximate noise channel is honest when it does not underestimate the actual noise, which means that here the distance between the approximate noise channel to the ideal channel here must be greater than the distance between the actual to the ideal channel. So here I will talk about the specific measure of distance in a later part of my talk. Basically, distance here can just be any measure that one can use to distinguish between the quantum channels. And the approximate noise channel is accurate if it closely mimics the actual noise channel. So which means that the error introduced due to the approximation here must be small, i.e. smaller than the actual noise in the system. Since we define the ratio here, the accuracy ratio by taking the actual noise divided by the error introduced due to the approximations, an accurate noise channel will then have accuracy ratio greater than 1. So here, our cluster expansion basically allows us to characterize how the accuracy changes as we include higher and higher order terms in the expansions. So at the end of the day, we can then use our technique to find what's the minimum number of qubits needed in the noise characterization if we want to achieve a certain desired accuracy of the simulations. So as an example, we consider applying our noise model for the simplest quantum error correcting code, 200 code. It has 2 physical data qubits, and it encodes 0 logical qubit, and it has 0 distance. Basically, it has data qubits which is in Bell states and is stabilized using these ZZ and XX stabilizers, and each of the Bell state here has unique syndrome measurements. And we consider applying this 200 qubit 000 code in a concrete realistic setup, which consists of processor built from fixed frequency qubits with static always on qubit coupling. And we use the realistic parameters for superconducting qubits in our simulations. And the C0 gates used here will be obtained by from the cross-resonance scheme, which is basically by driving the control qubit at the resonance frequency of the target qubit. And using these pulse schedules here, and with the realistic T1 and T5 here in the Lindblad master equation, we can simulate the actual noise channel. And then from the actual noise channel, we use the cluster expansion to get the approximate noise channel, as I described in the previous slides. And from the simulation, we can get the data qubit density matrix and the syndrome qubit measurements for 3 different quantum channels: noiseless, actual channels, and the approximate noise channels. And from this, then we can calculate the infidelity distance between any 2 of the quantum channels. So the infidelity distance here basically can be calculated from the fidelity between the syndrome qubit measurements and also the fidelity between the data qubit density matrix. Again, from these fidelity distances, we will calculate the honesty and the accuracy ratio, and we will choose the gain factor G that make the approximation honest for all of the input states, which is basically all the Bell states, and also maximizes the accuracy ratio, which is average over the 4 Bell states. And here is the results. So here you can see that the accuracy basically decreases as the number of runs increases, simply because of the accumulation of the noise decoherence effect. And the triangle geometry here basically is noisier than the linear geometry because it has 1 extra coupling between the qubits, which gives rise to 1 extra crosstalk channel. And most importantly is that if you compare the 2nd order and 3rd order approximation channel, the accuracy ratio here actually increases if you include the 3rd order correlated noise term, which means that the higher order term beyond the 2nd order correlated noise term can have a significant impact on the accuracy of the QEC performance. So in summary, I have presented the systematic approach for constructing honest and accurate approximate noise models. And by applying our noise model to realistic processors with always-on qubit coupling with realistic parameters for fixed superconducting qubit, we show that correlated noise beyond 2 qubits can have significant effect in the performance of the QEC. And our method is general and can be used for any quantum computing platform, and it also applies to multi-level qubit systems with leakage. And it principally can be used to quantify the smallest subsystem size that you need in the noise characterization in order to achieve a certain desired accuracy in the approximation of the noise. So, and that's all for my talk. Thanks.